This is a course on probability and statistics, or you could say it's a course on the science of chance. Now, once upon a time, it was thought that, well, chance is chance. What do you do about it? You're walking out in the open and then you get hit by lightning. That's chance. Actually, you can calculate the probability of that. And it's roughly equal to getting a 6 if you throw a die 8 times. That's the chance you'll get hit by lightning. It's only 400 years ago that we learned that chance can be studied scientifically, mathematically. And it came about because there were gamblers who wanted to maximize their profit. And so they learned clever strategies. For that, they had to understand combinatorics. From that came the concept of probability. And then it became a full-fledged science once mathematicians took over. Today, you can't do without probability and statistics in so many different professions. So, for example, if you work in a life insurance company, you've got to know what is the chance that somebody will die after the age of 65. You've got to know so many other things about your clients. Or if you're a process engineer, you want to know what's the chance that if I inspect only a certain number of items that I can reliably say that they pass the quality assurance test. But even more, if you work in quantum mechanics with atoms, molecules, quarks, gluons, then chance is fundamental because the universe is indeterministic. Quantum mechanics gives you probabilities that you need to calculate. So this course is going to be important for everyone. I'm going to begin with the very basics of the subject. Probability theory begins with the concept of random experiments, a sample space, and events which happen within that sample space. Let's see what they are. Of course, we are used to the concept of a deterministic experiment. So, for example, you could measure the angle between two lines, or how fast a body falls when it is released, or how much current flows when you apply a certain voltage to a wire. So these are examples where the same result will occur each time you do the experiment. However, in a random experiment, the outcome can be uncertain. Each time you do that experiment, you could get something different. This random experiment, however, must be repeatable. For example, you can flip a coin. It will land either on one side or the other side. You would then call the outcome a heads, in this case, a tail, in this case. Of course, it is possible that you could have a coin that lands on its side, in which case you would add a third outcome, heads, tails, side. But unless it's a very unusual coin, it will land either on one side or the other, and so there are two outcomes. Another example. Take a die. This die has got 1, 2, 3, 4, 5, 6 dots on its sides, and so we can call the outcome 1, 2, 3, 4, 5, 6. Of course, if you had different numbers of dots on these sides, these outcomes would have been correspondingly different. Now let's generalize. In any experiment, you can have different outcomes. Let's call them A, B, C, D, E. Now the set of all these outcomes is said to form what is called a sample space. So the sample space is the space of all possible outcomes. In the case of the coin, that sample space would contain 2 elements. In the case of the die, it would contain 6 elements. With each outcome in the sample space, there is associated what we call a probability. So P of A is the probability associated with A, P of B with the outcome B, and so forth. Now, in the language of mathematics, we say that there is a mapping from the sample space onto a number which is a probability. Each outcome has a definite number which is associated with it. Now, these A, B, C, D, E are simple events. So, for example, A could be the event that there is a 4 on the outcome over here of rolling a die. Now, A, B, C, D, E are what we call simple events. On the other hand, there can be what are called compound events. So, capital A could be event A as well as event D happening. I'll give you an example shortly. The sample space S, drawn over here, contains all possible outcomes. So anything outside of this sample space will have probability 0. It cannot happen. Now, to put this mathematically, P is a mapping. It takes a simple event such as A in the sample space S, and it gives a number P of A called the probability of A. Similarly, P of A, where A is a compound event, is the probability of that compound event. For example, take a normal die. In that case, the probability of having any number I, where I is 1, 2, 3, 4, 5, 6, is just 1/6. And, of course, if you add up all of these probabilities, that has to be 1. This is the statement that the die will land and it will give you any one of these numbers. For a compound event, such as A is 1, 3, 5, which means we are asking for the probability that the die lands with face 1, 3, or 5, then the probability of that compound event is simply the sum of 1, 3, and 5, rather the probabilities, and so that's 1/2. Similarly, if A was 1, 2, 3, 4, 5, 6, we would add 6 numbers over here, all of which are 1/6 and get 1. That's exactly what is being said here. At this point, it's necessary to do a quick review of sets. Now, the sample space S is a collection or a set, which is the set of all possible outcomes, which we've labeled here as A, B, C, D, E, F, G, H, etc., etc. In general, if you have a set, let's say A, which has got elements A and D, and a set B, which has got elements A, B, and E, these are called subsets of S. We then go on to denote the union of two sets by this symbol U, and the intersection of two sets by this symbol here. In the particular case of A and B as they are above, the union of A with B includes all the elements of A and all the elements of B, so we have A, B, D, E as the union of A and B, and the intersection of A and B, well, there's only A which is common to both, and so A intersection B is a set which has got just one member A. Now, of course, I've taken very simple examples over here. In general, sets can contain any number of elements. What if two sets have no common element? Then the intersection of C with D is the empty set. We denote the empty set with this 0 with a slash through it. In thinking about sets, it's very helpful to use what are called Venn diagrams. So this was a mathematician, John Venn, who died some 100 years ago. If this is the complete sample space S, then if A is a subset of S, then it lies within that sample space. And so this shaded area over here is the subset A. The complement of A, that is to say everything except A, has a bar on it. So the shaded area over here is A bar. You can think of the bar as saying not A. If we have two subsets of S, let's call them A and B, then the union of A and B is the shaded area over here. So, as in the case above, A and B, the union included all the members that belong to either A or to B, and so this shaded area belongs to either A or to B. And of course, the union can be drawn just as over here. So A union B is this area which is common to both A and B. It contains elements that belong to A and B. Now, from here, one can get so easily various different relations between sets. So, for example, there's the commutative law which says that A union B is equal to B union A. That is to say, the order doesn't matter. And you can look over here that if I took B union A, it would give you exactly the same shaded area. And so you can say that's a proof of this commutative law. Actually, it's very, very trivial here, but other relations will be not so trivial. We'll see them later. Similarly, A intersection B and B intersection A are exactly the same. Again, it's very, very trivial because A and B is the same as B and A. Here are some other obvious truths. So, for example, if I take A union B and take the complement of that, well, that's A complement intersection B complement. Can you see that? Let's look over here. Here's A union B. If I take the complement of that, that's the white space over here. On the other hand, if I take A complement, well, that's the white space outside of A. And if I take B complement, then that's the white space outside of B. Where they intersect, well, that's exactly the white space out over here. Similarly, if one takes the complement of A intersection B, that's the union of A complement and B complement. You can see that immediately by taking the complement of A intersection B, that is to say, take the complement of this part over here, which means all the white stuff here, 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 and that's exactly what's on the right-hand side here. And this, of course, is totally obvious that if I take the complement of the complement, then I get back the set itself. Now, what if I take the complement of the entire sample space? So, the complement of the sample space is the empty set, which we've denoted over here. That's the notation for the empty set. And of course, if we take the complement of the empty set, we get the full sample space. That's what's over here. If you take the intersection of the sample space with any subset A, well, obviously, that is going to be A itself. And finally, if you take the union of S with any subset A, that's S. Now, to get a little bit of practice, I would suggest that you take some paper and pencil and actually just draw this and convince yourself that this is true. Mathematicians might want to do the proof more formally, but at the end of the day you get the same result, and it's not very much more useful to do it the other way, the formal, rigorous way, as compared to using Venn diagrams. Now, this was all pretty much trivial because we were dealing only with two sets. What if there are three sets? There we will encounter something new and different. Generalizing our experience with two sets, now with three sets, we'll call this part over here as A intersection B intersection C. So this part over here contains elements that are common to all three, A, B, and C. Read this as A and B and C. The complement of this, so imagine that you were to put a bar on top of this. Well, that's exactly equal to A bar union B bar in union C bar. Again, the picture tells you why it's true. Let's explore further. So here is A intersection B bar intersection C bar. Clearly, it includes elements that belong to A, to not B, and to not C. So that's the part over here. All this stuff here, all elements that lie within this part that I'm highlighting with my cursor. Here's A intersection B intersection not C, or C complement. Again, you can see that every element over here belongs to A and to B, but not to C. So you've got pretty much the hang of it now. So this is the part over here that doesn't belong to A, doesn't belong to C, but belongs to B. Over here, the elements that are in this part over here belong to B and to C, but not to A. And here, obviously, all the elements over here, like this, belong to C, but not to A and not to B. And to complete this, we have A intersection B complement intersection C, and that's the part over here. All this is going to come very useful once we talk about probability, because probability is defined upon sets. Venn diagrams are also very useful in establishing certain laws, such as the associative law, which says that A union B union C, you can write like this. That is to say, it doesn't matter where you put these brackets. All the elements in the set here and all the elements in the set here are exactly the same. So these two sets are equal. Similarly, if I take A intersection with the intersection of B and C, well, that's exactly the same as this. A intersection B, intersection C. The Venn diagram also helps you establish the distributive law, which says that if I take B intersection C and take the union of that with A, then I'll get this on the right-hand side. And that's actually very easy to see. What you do is you establish that there's the same shaded region on the left side as there is on the right side over here. And I'd say that you should spend just 1 minute trying to do that. And it's pretty trivial because B intersection C is what's common to both B and C. And now the union of that with A means that you've got to include the part of A as well as this over here. And now do the same for the right-hand side and you'll come up with this as well. You'll do this similarly. There are other obvious truths as well. So, for example, if I take A union B union C and take the complement of that, well, that's equal to A complement intersection B complement intersection C complement. And actually, I did indicate this on the previous slide. Similarly, if I take the complement of A intersection B intersection C, that's equal to this. It'll take you less than 1 minute to establish that or to establish this. There are lots of other such relations. One doesn't have to remember them. Derive them as you go along. Let's now take some definite examples of random experiments, sample space, and events. Consider 3 coins of 1 rupee, 5 rupees, 10 rupees that are flipped. What is the sample space? Well, in each case, you'll get a heads or a tail. And the sample space contains 8 elements. Heads, 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 all the way down to tails, tails, tails. These, of course, are all possible outcomes. Now, suppose we call event A as whenever the 10 rupees coin lands head up. Question: what is A? Obviously, A comprises these 4 elements, these 4 occurrences. In each case, there's a head, 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 but then it could be head, 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 tails, tails, head, tails, tails. Well, let's take now another example. What is the sample space that corresponds to rolling 3 dice? In this case, the sample space contains too many elements to write down, so you can easily see the first outcome is where the first die has a 1, the second and the third all have 1s. The total number of elements in this set, or what you call the order of the set, is 6 into 6 into 6. That's all the possibilities, and that amounts to 216 simple events. Well, let's go on to a compound event. An event A is defined as happening when the sum of 3 throws is 17 or more. The question is, what is A? In that case, A is this set: 665, 656, 566, 666, and you can see that in this case the sum is 18, in this case is 17, 17, 17. Obviously, this A is a subset of the sample space S. What is the sample space for a free particle that moves between x equals 1 and x equals 4? Now, this is the first example that we are encountering where the number of outcomes is actually infinite. The sample space is all values of x where x lies between 4 and 1, inclusive of the points x equals 1 and x equals 4. Now, this is an infinite set because, of course, between 1 and 4, there are an infinite number of points. In most cases, this doesn't bring up any particular complications, and we learn to deal with continuous sets. It's actually quite easy. Of course, here you will define events somewhat differently. So event A could be defined as whenever the particle is between 2.5 and 3.7. Question is, what is that event A? And obviously it is A is that set of x where x lies between 2.5 and 3.7, the points 3.7 and 2.5 being included. Now that we have a clear understanding of the sample space as being a set and events being a subset of the sample space, we can go on to discuss probability. Probability can be given 3 different meanings. One of these is a very subjective one, so it's an opinion. That opinion is that there is 40% probability of nuclear war in South Asia by the century's end, but less than 25% in Europe. Of course, nobody really knows, nobody can calculate. This is just an opinion, just like any other opinion. For example, I could say, oh, the chance of that bakery having fresh bread is 90%. Again, there's no real way to assess it. You could look at probability as relative frequency. If A is an event, doesn't matter whether it's simple or it's compound, if that event occurs n times in a trial that's repeated n times, then the probability is then the limit over here. What this means is that the number of times A occurs divided by the number of trials n. If you do a large number of trials n, then this ratio is what you call the probability. So, for example, if I take a coin and I flip it again and again and a very, very, very large number of times, then half the number of times it'll land heads up and half the number of times it'll land tails down, and we'll say that the probability is half. Similarly for die and so many other repeated experiments. Now, the classical or the most usual definition is that if A is an event, then the probability P of A is the number of ways that A can occur divided by the number of elements in the sample space S. So this is fine, but mathematicians need something even clearer. And this will take us to the axiomatic definition of probability. This axiomatic definition is rigorous, so you can apply mathematical rules to it, and it's very easy to show that it includes both this definition as well as this definition over here. So let's go on to the axiomatic definition of probability. I've already hinted what probability is. It's really a mapping from the sample space S. So it takes elements of this sample space S, which are events, and it maps them into numbers. P of A, P of B, C, D, E, etc. That mapping obeys certain obvious rules. The first rule is that the probability of an event A always has to be positive or zero. If P is zero, that means that event will never happen. And we note that any subset of S is an event. So if that subset contains just this element A, well, that's an event, but another event could be that event in which A, C, or maybe E are all together would be called a compound event, as we called it earlier, and that will have a different probability. Sometimes there's a little confusion, so please note, if there's a subset of S, in this case it contains only the element A, then P of this and P of A, although strictly speaking they mean different things, but they correspond to the same number. Here you should simply think that we have been lazy and omitted the symbol for set. Next, if we have two disjoint events A and B, that is to say, the intersection of the set A and the set B is zero, then the probability of their union is just the sum of the probabilities. Note that we insist over here that A and B have nothing to do with each other, that they are separate, disjoint events, that there is no intersection between them, and we can also say that these are independent events. This obviously generalizes, and so if I have the probability of any number of disjoint events, A, B, C, D, E, F, etc., the probability is just the sum of the separate probabilities. Now remember, this is an axiom. This is what we take for granted, and it makes a lot of sense. The third axiom is that the probability of the entire sample space is 1. So if I take P of S, that's equal to 1, which says that certainly something will happen. So if I flip a coin, I'll definitely get either a head or a tail. And there's no provision over here for the coin going missing. Now, if you want to say this more formally, then you can write P of A plus P of B plus all the other possibilities. The sum of those probabilities has to equal to 1. Obviously, the probability of nothing happening is 0. That, of course, is the same as saying the probability of the complement of S, the sample space, is 0. These three axioms distill for us the very meaning of probability. We will now explore the consequences of these axioms. The simplest ones will be discussed here. So, let's take any subset A of the sample space. The union with its complement is the full sample space, and obviously we have the probability of A union A bar is equal to 1 because P of S is 1, and so P of A plus P of the complement of A is equal to 1. But there's a nice different way of looking at this. This says the probability of an event not happening, that is to say P of A complement, is 1 minus the probability of that event happening. Sometimes it is easier to calculate P of A, and sometimes it is easier to calculate P of A bar, but in any case, if you know one, you know the other. Now, sometimes it is helpful to view things pictorially using Venn diagrams, and now I'll use colors over here. For this set A, it's colored green. The set B contains the set A. This symbol over here says that B is a set that's bigger than A. That is, every element of A is included in B. Or, of course, the two sets could be the same, in which case you would have the equality between them. Now, if you look over here, this is A, this is B intersection the complement of A. And so this colored area over here is B intersection complement of A. And now this and A have no element in common. In other words, they would be independent events. So let's write B in the following way. B is A union B intersection A bar. And so by the second axiom that we saw, the probability of B can be written as the probability of A plus the probability of B intersection A bar. As I stressed over here, with this diagram you can see that B intersection A bar has no elements in common with A, and so this follows the sum of two independent events. Now there's something that's obvious that follows from this, that the probability of B is greater than the probability of A. That's because every probability has to be a positive number or equal to 0. It also makes a lot of sense. If B is the bigger set, then the chance of B happening has to be greater than the chance of A happening. Next, let's look at the following situation where we have a set A and a set B. There's some intersection between them. We want to ask, what is the probability of A union B? That is to say, an element of this set, A union B, belongs either to A or to B or to both. To answer this, we will make use of the axiom that the probabilities of independent events can be added up, but here A and B have elements in common with each other. So there is an intersection here. Let's now look at this, A intersection B bar. So this is all the elements that are over here. Note that this set has got no elements which are in common with B. Let's write A union B as A intersection B bar union of B. Okay, so now we use our axiom. The probability of A union B is then just the probability of this plus the probability of this. Now we're almost there, but we need to write A differently. A can be written as A intersection B bar union of A intersection with B. All you have to do is look at this Venn diagram over here to see that A, which is here, all this over here, including this, well, that's the union of this with this. So P of A is just the sum that you see over here. Okay, but you've already seen this earlier over here. And so this equation can be continued over here. Now we have P of A union B minus P of B plus whatever we had before. So basically what I've done is I've said that this is equal to this minus P of B. Well, now we've got basically what we wanted. We've discovered that P of A union B, which is what we wanted, is the sum of the probability of A and the probability of B. And from here you have to subtract the probability of the intersection of A with B. And so suppose that A and B are independent events, which means that there is no intersection, which means that this over here is the empty set, which means that this is equal to 0, in which case we would have the probability of two independent events A and B and just be the sum of P of A and P of B. You can see also from here that because this over here is a positive number or 0, therefore the union of A and B, the probability of that will be less or equal to P of A plus P of B. Now this result can be generalized to any number of overlapping sets, and we'll take three sets over here, A, B, and C. And you can see that there is overlap between all of these sets, A with B, B with C, C with A. We want to know what is the probability of the union of A with B with C. Well, of course, we can write this in the following way. This is A union B, union C, and it doesn't matter what order you take it. This is the associative property of sets. Okay, so we just learned that if we have two sets, and if the sets do have an intersection, then we know how to write this probability, and that is the probability of A union B plus the probability of C, but then you have to subtract from it the union between this and C. Okay, so let's repeat that rule once again. We have the probability of A union B. Let's write that as P of A plus B of B minus P of the intersection of A and B. We'll write P of C the same as above, and then we are left with this. Now, what we have over here can be written just as before in this way. Remember that we had used a Venn diagram to establish the set relationship, which is over here, and prove that equivalent to the set over here. So now we've got our result. That's because PA, PB, PC, well, they're over here as before. I've written this back over here, and now here we have a union of two sets. One is this set, one is that set. Now we use the rule that we had derived earlier, so it's the probability of this set plus the probability of this set minus the probability of their intersection. Well, that minus turns into a plus, and so we have the final result that the probability of A union B union C is equal to this. So basically this says that you just add up all the probabilities, then you subtract those parts which are common to the intersecting sets, A with B, A with C, B with C, but then you've subtracted too much, and so you've got to add on this part over here. This part over here is essentially this. So the probability of this had been over subtracted, and we are restoring that with the plus over here. Now you can easily generalize this to 4 sets, 5 sets, any number of sets. In every case, you will have one line over here, which is the sum of the probabilities, as though there was absolutely no intersection between any of the sets, and then correct for 2 of them intersecting, then correct for 3 of them intersecting, and then add in the final term where you've basically put back what has been over subtracted. We've looked at sample spaces and events. Now let's actually calculate some probabilities using them. So this is the earlier example of 3 coins of 1, 5, and 10 rupees which are flipped. This is the sample space for that. Let's look at the probability of event A, where event A is whenever the rupees 10 coin lands head up. And that is this set with 4 elements in it. The sample space has got 8 elements in it, and so by our rule that the probability is the number of ways that A can occur divided by the number of elements in the sample space S, well, that is then 4 over 8, which is 1 over 2. Let's go to the second example that we had taken. That corresponds to rolling 3 dice. The sample space was this. It had a lot of events, 216 simple events, and then we defined a compound event as when the sum is 17 or more. We found that that compound event corresponds to a set which has got these 4 elements in it. So then, the probability of the event A is simply the number of ways that A can occur divided by the number of elements in the sample space S. That's 4 over 216, that's 1 over 54. And finally, let's look at the third example. The sample space for a free particle between x equals 1 and x equals 4 was simply the set of x lying between 1 and 4. If event A is defined as being whenever the particle is between 2.5 and 3.7, then this is the event. Event A is the set of x, where x is between 2.5 and 3.7. And now, suppose one asks, what is the number of ways that A can occur divided by the number of elements in the sample space S? Here we run into a little problem, because what we want is the number of points in this interval here, and we divide by the number of points between 1 and 4. Now, it doesn't make the slightest difference whether you include the endpoints or not, because the number of points between any 2 points on the real line is infinite. And so basically you're left with infinity over infinity, and you have to give this meaning. Now, one way of giving this meaning is to say that this is the length of the interval between 2.5 and 3.7 divided by the length of the interval between 1 and 4, and so that's 1.2 divided by 3, and that's 0.4. And this certainly makes a lot of sense, but it's not very rigorous from the point of view of mathematics, in particular that which is called measure theory. We will have to get a little more sophisticated in order to handle continuous probabilities, but that will come a little bit later.